Now one more examples where we're looking at the convergence of series, and we want to show in two different ways that the series from 1 to infinity of n e to the negative n is convergent. One of the first criteria that we have studied to decide about the convergence of a series was to compare the series with an integral. And here we have the series of terms of the form f of n, where f of x is x e to the negative x, which is a function for which we can calculate the integral. So it is a natural way to study this series. So we can try to use the integral test. Here the function that we would have to look at is x e to the negative x. And just to remind you the assumptions in the integral test, this applies to functions that are non-negative, continuous, decreasing, at least eventually decreasing. And in our case, we have a positive continuous function that is decreasing on the interval 1 infinity, because the derivative, if you use a product rule, you get 1 times e to the negative x minus x times e to the negative x. So factoring e to the negative x, you get e to the negative x, which is a positive number, multiplied by 1 minus x. And of course, 1 minus x is negative when x is greater than 1. So the function is decreasing. That means that the integral test applies. In other words, the series is convergent if and only if the integral of that function on the interval 1 infinity is convergent improper integral. So we look at this improper integral. By definition, this is the limit as t goes to infinity of the definite integral from 1 to t of x e to the negative x, which we can calculate by parts by differentiating x and integrating e to the negative x. So when we integrate by parts, we get uv, that's negative x e to the negative x, that we evaluate between 1 and t. And then we subtract the integral of v du. So we subtract the integral of negative e to the negative x dx. So I get plus the integral from 1 to t of e to the negative x. But that's really the antiderivative of e to the negative x, which is negative e to the negative x, evaluated between 1 and t. So we can write that as negative x e to the negative x minus e to the negative x, evaluated between 1 and t, and factoring negative e to the negative x. This is what we get. If we plug things in, the value at 1 is negative 2 over e. So since we subtract the value at 1, I get 2 over e. And then the value at t is negative t plus 1 over e to the t. And now we want the limit of this expression as t goes to infinity. And the second term, the term that depends on t, turns out to go to 0, and therefore the limit is 2 over e. The reason why the second term, t plus 1 over e to the t, goes to 0 is because applying the rule of de L'Hopital, we have a ratio, an indeterminate form of the type infinity over infinity. When I take the ratio of the derivatives, I get 1 over e to the t, which goes to 0. So the limit of my expression is 2 over e. In other words, the integral from 1 to infinity of x e to the negative x is equal to 2 over e. It is a convergent integral. And therefore, by the integral test, the series is convergent as well. Now, an alternative way to deal with that would be to use the ratio test. Because really, when we look at e to the negative n, you can think of that as a power, and so the ratio test might be useful. Well, if we look at the ratio of two consecutive terms, an plus 1 over an, get n plus 1 e to the negative n plus 1, which I can write n plus 1 divided by e to the n plus 1, and then the reciprocal of an, so that's 1 over n e to the negative n, but this e to the negative n at the bottom, I can write it as e to the n at the top. And you see that e to the n divided by e to the n plus 1 is really just 1 over e, so we end up with n plus 1 over n multiplied by 1 over e. And when n goes to infinity, n plus 1 over n goes to 1, and therefore the limit at infinity of my ratio is 1 over e, which is less than 1. So we can conclude by the ratio test that the series is convergent. As you can tell, this is more efficient than using the integral test because we don't have to calculate explicitly an improper integral. So sometimes you have various ways to conclude about a series, and it is good to reflect about what is most efficient. In particular, the integral test is sort of a last resort because the other criteria that we have seen typically require less work to conclude. Now, before we turn to the second part of this module, the root test, we're going to go over an exercise that is slightly different because we're asking about the convergence of a sequence rather than a series. We're looking at the sequence of general term x to the n divided by n factorial. So that depends on x. So we fix a particular value of x and then look at these powers of x divided by n factorial. So x to the n over n factorial. And we want to know if it's convergent, when it is convergent. So for what value of x is it convergent, and if it is, what is the limit? So we're looking at a sequence, not a series. But we could look at the behavior from the same viewpoint as a ratio test. In other words, look at the asymptotic behavior of the ratio of two consecutive terms and hopefully see if it behaves in a way that is comparable to a geometric sequence. So if we look at this ratio of consecutive terms, an plus 1 is in absolute value of x to the n plus 1 divided by n plus 1 factorial, and I multiply by the reciprocal of the absolute value of x to the n over n factorial, which is n factorial divided by absolute value of x to the n. Now you see that n factorial over n plus 1 factorial, I have the product of the first n integers that I divide by the product of the first n plus 1 integers. They're all going to cancel out except n plus 1 at the bottom. So I get 1 over n plus 1. And then I have this ratio absolute value of x to the power n plus 1 divided by absolute value of x to the power n. Of course, absolute value of x to the power n plus 1 is just absolute value of x to the power n that I multiply again by the absolute value of x. So absolute value of x to the power n cancels out, and what remains is just absolute value of x. And now, what is the asymptotic behavior? What happens when n goes to infinity? Well, 1 over n plus 1 goes to 0, and since x is a fixed number, absolute value of x is just some fixed number, so the limit is 0 regardless of what x is. Well, that's interesting because that means in particular that if instead of the sequence I was looking at the series of general term x to the n over n factorial, then this series is convergent, in fact absolutely convergent, whatever the value of x is, according to the ratio test. Because the limit of the ratio of two consecutive terms is 0, which is less than 1. But if the series is convergent, that means that the sequence of general term has to go to 0, right? Because this is essentially what the nth term test tells us. If we have a convergent series, then the sequence of terms necessarily goes to 0. Usually we use it the other way by saying if the sequence of term does not go to 0, then the series cannot be convergent, therefore it's divergent. So here what we have concluded is that for all values of x, this sequence has limit 0. But to reach this conclusion about the convergence of a sequence, we looked at the associated series. In the next video, we're going to discuss an alternative to the ratio test, but which is essentially in the same spirit of comparing your series with a geometric series.